We're looking at 3D vectors, unit vectors and vector components. Let's firstly look over here on the left hand side of the screen. From our previous work, geometric vectors, let's say the directed line segment A to B, we could call that a letter U, U with the little tilde under it. And one of the things we've seen is that there are many representations of U. As long as it goes from starting point to end point, it goes across a certain number of units and also up a certain number of units. The resultant is AB. But of course we can write that anywhere we like. We can translate that around. So provided we don't change the length of AB or the length of U, and we don't change its direction, we have an infinite number of different possibilities. And here we can see just three of very, very many that are possible. While that's an easy thing to understand for most of us, the problem is it can cause misunderstandings and ambiguities. So let's look at this idea of vector components and unit vectors. In the second diagram, we can see we have vector u again. It's the same vector u essentially, but we have a understood fixed position which we call the origin. You know that word from your work on Cartesian Plane. If we understand that this known origin is where vector u starts, we can apply this idea of unit vectors. Now we're looking at a two-dimensional situation first before we move on to three-dimensional. So we can look at any two-dimensional vector as being made up of multiples of unit vector I and unit vector j. We'll talk about what these unit vectors are in just a moment. So if we know that back over here on the left hand side that from A to B we went 6 across and 3 up, 6 across and 3 up, using the system of unit vectors we could express u over here as 6i plus 3j. A unit vector has a length of 1 unit. So we would say vector u is 6i plus 3j. Formally identifying and defining unit vectors now. A unit vector is a vector of length 1 unit. In two-dimensional systems, like this flat screen or your piece of paper, a unit vector uses I and j. Now that's either written like here, you might be able to see that these are in bold. You can't write in bold, like for example with pen and paper you use the tildes. They are vectors in their own right. They have a length of 1. I goes in the x direction and j goes in the y direction, as you can see over on these diagrams here. So vertical is the y direction, so j unit vector corresponds with that, and x is the horizontal direction in most systems, and I corresponds with that. If we have some two-dimensional vector which we'll call A, you can see it there in bold, or I'll write the tilde version there. The unit vector of that is called A hat, because of the little hat on there. So the hat is a little sharp arrowy type thing, arrowhead, and that means the unit vector in the direction of A. So the magnitude of any unit vector is 1, and the magnitude of A, which is purely the length, that's a scalar, so those two signs mean the magnitude or the length, or magnitude. Magnitude is the better word, that's the one you'll hear. The length times the unit vector, which is a vector of length 1 in the direction of A, equals A. That makes sense. If you get the direction and length 1 times the actual magnitude or the length, you get the actual vector itself. another way of looking at this is to get the unit vector, you divide any given vector A by its length or its magnitude. So that's just a rearrangement of above. Sometimes it can be written like this here. So the unit vector of x, where x is a vector purely in the x direction, is called I. Its magnitude is 1. The one in the y direction is called j. And when we get on to the 3 dimensions, we'll see z and k. So you can see there, just if we have a vector A, you can see its direction. I like to put the arrowheads there, not in the middle. The unit vector of that is the same vector direction, but it only has a length of 1. That one there has a length of 1, whereas this has a length of whatever the magnitude is. So if we can get back to this idea of the vector u that we started with, this one here, we did several things with it before. If we can get back to that and call that some vector in general, so u would be written in this way. Okay, that's called Cartesian form of a vector. That should make sense. Cartesian has a capital C. Cartesian form of the vector. Alright, you can see that it uses the Cartesian axis, so that makes sense. And it'll be some value, some scalar there for x and some scalar for y. If we apply the one above, it would be x would be 6 and y would be 3. So we would have u equals 6i plus 3j. The magnitude or the length of the vector, if it's a geometric vector, but try and use the word magnitude, it is a better, more precise word to use, because we're not only dealing with geometric vectors all the time. It's not the only form of a vector. So the magnitude, the size, the length are all synonyms for that. Okay, if we have this vector xi plus yj, you basically use Pythagoras Theorem. So that's the symbol for magnitude of vector u, which is a scalar. Alright, and we go x squared plus y squared, take the square root. Okay, those being x and y. So it's just an application of Pythagoras Theorem, because you can see up here that that's a right angled triangle essentially. Geometrically it is. Now the good stuff. Well, a lot of people consider this good stuff because we live in a three-dimensional world. Computer graphics like to mimic 3 dimensions. So do a lot of dynamics of video games, even though they are still on a 2-dimensional screen. Virtual reality is still 2-dimensional. Any really good graphics on a TV or a monitor or any sort of screen are 2-dimensional, yet they can be viewed as 3 or perceived as 3. How does it happen? Well, I can't tell you the answer to that in full on this video, but this is the beginning of that. Additionally, many things, just to use some examples like navigation, can use 3-dimensional vectors. So, if you grab your right hand out, and you might be able to even see on the screen here. Okay, so I've got mine out there. Can you see down the bottom corner? I wonder if that's coming through on the video. Grab your right hand, hold it out. Don't grab your hand, sorry, just hold your hand out. None of this grabbing stuff. What am I talking about? So basically, your thumb points up, your index finger, that's your first finger, alright, for the finger illiterate out there, and your middle finger, yeah, well, you've probably used that before. Basically hold them out like that, and that's called a right-handed system. Right-handed systems get used for a lot. This is where it starts. You'll probably hear right-handed systems used for a lot of things, especially if you study science, engineering, mathematical based things. Okay, so that's basically the system that underpins 3-dimensional vectors. If you rotate your hand around, I wonder if you can see me there. It's not very good on a webcam, but it still remains, as long as you hold your fingers static and you just rotate your wrist, don't move your fingers, Alright, it'll always be a right-handed system. You can see that we can do some beautiful things with our three-dimensional right-handed system. So if we call this one the z-axis, now have you heard of that before? And this one here would be the x-axis. This is the other end of the x-axis. This is the other end of the z-axis. And where's the y-axis? Well, I'm glad you asked. There it is. Now these can vary, these systems, but it always remains a right-handed system. Things can rotate around. Now the Cartesian plane you've been doing for a long time in your maths classes, probably ever since primary school, we usually look at that as vertical, don't we? Like, there you go, there's our x and y axes, and I know how to plot things, and you probably remember when your life was enriched when the teacher showed you the negative ones. Whoa, 4 quadrants and so on. You did start off there, didn't you? Now, that's standing up on the screen. If you can imagine that laying down flat, and you can see that over here, this y is now laying down flat over here. It's like our perspective has changed. So instead of seeing it front on, if we see it from a different perspective, if we're up here looking down on it, you can see it's still there. There's x and y. And z pops up. So you can't show that on this picture. It would pop into the screen, wouldn't it? And it'd go into the screen and pop out of the screen. So it's the in and out of the screen thing which we can't show, but on a 3D diagram we can show it. So that's pretty cool. We have all these different directions, so the z is popping in and out, the x is going across, the y is going along that direction, which used to be up on the old piece of paper. So we have 3 dimensions. And we can see planes, P-L-A-N-E, which are surfaces. There's a plane there, which is purely basically along there, okay? And then there's a plane that stands up there. So we can also create different planes on the 3D system. There's a couple of examples. Linking back to what we earlier did on storage vectors. You might have noticed the storage vectors we saw previously just had 2 numbers. They were all 2-dimensional, so where A is some number and B is some other number. This is the 3-dimensional one. It's simply the same idea where you've got x, y and z, and as an extension on what we saw, if A here is a 3-dimensional vector, it's written in Cartesian form as xi plus yj plus zk. Make note of that. I, j and k are unit vectors, so it would make sense that I, j and k are written like this. That there is good to understand, but it's not particularly important. However, this is important. I wonder if you can guess what the magnitude of a 3-dimensional vector would be. Pause the video and have a think. Well, let's have a look. If we have xi plus yj plus zk, where x, y and z, are real numbers. As an extension on the previous formula for the magnitude, we have that formula there. So it's really just the same. Instead of x squared plus y squared, we've got x squared plus y squared plus z squared, then take the square root. So Pythagoras' theorem does work in 3 dimensions. So this may be something new there. Okay, another important point, so the unit vectors would sit on our right-handed system like this. Now notice that there seems to be a difference between these 3D right-handed systems. Well, there's not. They all have the same relationship. They're all at right angles to each other, but it depends where you rotate it. Back here, y went into the page, x went out to the right, and z went up. Over here, it seems like a different system, but they all have the same relationship. You could get it to the same as the system above by just rotating. It's important to understand that they're all the same system, but rotations can happen. So note that there are two different conventions for drawing three-dimensional axes, x-axis to the right or y-axis to the right. They're all valid, they're just rotations. That's not a big issue when it comes to doing questions that property, but do be aware of it so that if you see variations you won't freak out. Let's look at a couple of examples and then that'll be it. If we're given that vector A here equals I plus j minus k, vector B is I plus 7k, find A plus B. So that's vector A plus vector B. To add vectors, we add the corresponding components. I've written in general the pattern here. If we have two vectors A and B, but they're both in Cartesian form, like these two up here, we add the x value in A to the x value in B, and that together is added and becomes the coefficient of I. Y of A and y of B is added, and that will be the real number scalar before j, and ZA and ZB is added and it appears before k. So basically we add the corresponding components. So for A plus B, you can see the solution done here. A has, now you're thinking, where's the number? It's just an I. Well, that's one I. So you've got to think a little bit algebraically here. Just like x is 1x when you do algebra. Well, it's the same. That's one. So we've got one I plus one j. Sorry, one I plus one I, pardon me, is 2i. 1j plus, there's no j. Is this a two-dimensional vector? Are we trying to add one and two-dimensional vectors? The answer is no. It is a three-dimensional vector. What about the y? Well, the y is 0. So that'll be 0j, which is understood and we don't need to write that. So really, it's 1j plus 0j, which is 1j. And you can see that 1j is written there, just this j. And we have, be careful of your negatives. Okay, we have negative 1k plus 7k, which is positive 6. Skipping now to the last part there, the thing we've got to find is the magnitude of A. Now it's not worked out, the answer is square root of 3, but how do they get that? Well, magnitude of A, remember we use Pythagoras Theorem, so we look at what's the x value there, it's 1, so it's 1 squared. What's the y value? It's also 1, it's 1 squared. What about the y value here? It is negative 1 plus, be careful, negative 1 all squared. Please put the brackets around that, otherwise you'll get the wrong answer. Okay, so we have 1 plus 1 plus 1, which is the square root of 3, and that's the exact value of that. Finally, in our last part of this video, we have here some things. It's a 3D system. A is located by moving from the origin 1 unit along the x-axis and then 2 units along the y-axis and then 3 units along the x-axis, it says up here. So we can see that the point would be 1, 2, 3, that the end point is, but the actual vector would be written as 1i plus 2j plus 3k. And if we drew that in, which is a little bit tricky to do with a tablet and a stylus, alright, that's the vector. So from the origin there, that would be the geometric vector. Sorry, I'm trying again. Okay, B, likewise, 2 units along x, which is 2i, 1 unit along y, which is 1j, and 3 units along z-axis, which is 3k. Okay, and you get vector B, likewise, we can see that up here. Trying to show you in blue there. Okay, so it's a three-dimensional system